So let's continue. Um, so I'm gonna talk about the superposition also for electric field, and instead of like talk about the theory, which actually is pretty simple, I'm gonna do the same problem that we did last time, but I'm gonna do it using electric field. Okay. So what did we do last time? So last time we have this problem. Remember, like we have a square and we have many charges on the corner of the square. So we have Q1 here, which is, if you remember, 1 microcoulomb. And then we have Q3, which is minus 2 microcoulomb. And we have Q4, which is plus 1 microcoulomb. And then we have Q2 here, which is minus 1 microcoulomb. And the distance between each charge, well, the side of the square is 1 centimeter. So the question that we asked last time is, what is force F2, which is force on Q2? And the way we did last time is we used Coulomb's force and write down force from each pair, and then we add up the three forces like the way we add vectors together. In other words, we add them vectorially. Okay, so we're gonna do the same thing here, but we're gonna do with electric field. So let's ask first, like, what do we need? We want to know the force on Q2. So according to F2 equal to Q times E, Q2 times E, what we need is Q2, that's given. We also need electric field at the location of Q2. So we need electric field at this point, at this location, at this position. So how do we calculate that? Well, the electric field at location of Q2 comes from three other charges, Q1, Q3, and Q4. And all of them gonna give different magnitude and different direction. So you need to combine them together, combine all the electric fields from every single charge other than Q2 together. Once you have that E, which is the net electric field, then you just multiply by Q2 and then you get force force F2. And hopefully we're gonna get the same number as last time, right? So the superposition principle is used when we combine the electric field from other charges together, right? So it's the same concept as what we did last time when we combined the forces. So at this point, actually, we can just forget about Q2 at the moment, because remember, we need the electric field at this location. So it has no reference to Q2. So we can just remove Q2 for a moment and then draw and write down the electric field from each one. So let's start with Q1. Q1 is positive, so electric field from Q1 gonna point away from Q1. So E1 gonna point that way. That's E1. Now what about Q3? Q3 is negative. So the electric field gonna point towards Q3. And I'm gonna write it E3 because it's the electric field from Q3. And Q4 is positive, so it's gonna point away from Q4. So Q4 gonna give E4, which is that direction. So we know the direction of E1, E3, and E4. Let's write down the value for the magnitude. So the magnitude of E1 is K Q1 divided by R squared. Remember what K is? K is about 9 times 10 to the 9 in SI unit. So I'm not going to write the unit because we just remember that we use SI unit. Q1 is 1 microcoulomb, so it's 1 times 10 to the minus 6 coulomb. Divide by distance square, and distance is 1 centimeter, so it's 0.01 meter square. Right, so it's the side of the square. So I calculate this. And what I get is quite a big number. So the electric field is 9 times 10 to the 7. What's the unit again? Newton per coulomb. So it's quite strong, large electric field. But that's fine. What about E4? E4 is the same magnitude as E1 because the distance is the same. The magnitude of the charge is the same also. So it's still 9 times 10 to the 7 Newton per coulomb. What about E3? E3 is coming from Q3, which is double in size, but it's a little bit further away. So, and again, I just ignore the negative sign because the negative sign of Q3 is only relevant when determining which way E3 is pointing. We already figured that out, so we just need the magnitude at this point. So times 10 to the minus 6 coulombs and divide by the distance square. Well, the distance is 0.01 meter times square root of 2, right? Because it's the hypotenuse of this isosceles right angle. So that's what you have here. And when you calculate this, you actually gonna get the same magnitude. So I chose the the amount of charge such that all the electric field have the same magnitude. But remember, they point in a different direction. Okay, so let's combine them. So they are the same magnitude. So E1 is pointing, not E1, this is E4, pointing up. E1 point this way. E3 points this way. Okay, like this. I'm just copying what I have here, but maybe a little bit more to scale. And then you have to add 3 of them like you add vectors. And well, I'm not gonna spend too much time repeating kind of similar to what we did last time. But in the end, the resulting vector, which is the electric field, gonna point that way. This is what we call E total. Just to make clear that what we are talking about. So E total is a result vector from E4 vector plus E1 vector plus E3 vector, and then you get that one. Right, so you can check this. And I'm not going to repeat the geometry, but you can probably trust me that it's going to point that way, which is 45 degrees. And the magnitude is, well, I just put in the number, times 1 minus root 2. And the result is 3.7 times 10 to the 7 Newton per Coulomb. So it's pointing that way. Okay, so it's pointing in the northeast direction with the magnitude of 3.7 times 10 to the 7 Newton per Coulomb. So this is the electric field at the location of Q2. Now if we want the force Q2, force on Q2, which is F2, this is easy because we know the electric field. So we just need to multiply Q2 with E total here. Okay, so just to be absolutely clear, I'm gonna write again what is E total. E total is the electric field from all charges other than, of course, Q2, because Q2 is the one we want to calculate the force, combined together. And in this particular case, because we only have 3 other charges, is E4 plus E1 plus E3. That's E total. So what is Q2? Well, Q2 I kind of erased that already, but it's minus 1 microcoulomb, so it's 10 to the 6 coulomb times E, which is 3.7 times 10 to the 7 Newton per Coulomb, and it's in the 45 degrees northeast direction. So if you calculate this, you get minus 37 Newton in the northeast direction, or you can just flip the sign. You can say it's the 75 Newtons in the southwest direction like this. So you can see that it's the same answer that what got last time. What is E3? E3 is also 9 times 10 to the 7 Newton, but the direction is southwest. Right. So all of them has the same magnitude because E3 is from Q3, right? But Q3 is a little bit further away. So it's a little bit weaker, but Q3 is also double the amount of charge. So those kind of offset each other. So this is E3. Is that okay? Okay, cool. So you got the same answer that's what we got last time as what we got last time, which is good because, you know, that's the way it should be. But this is a different way of calculating, is that you calculate the electric field first, and then you kind of put the last step to be this. Why this is more convenient is because you can replace Q2 with any other charge, and you don't need to repeat the calculation again. For example, I say like, okay, let's repeat this calculation, but now Q2, which is here, let's change from minus 1 microcoulomb to plus 10 microcoulomb. What's the force on Q2 in this case? If you do it the same way as what you did last time, you need to recalculate the Coulomb force for every pair again, and then you just need to combine them. But in this case, we have the electric field at the point Q2, at the location of Q2. So if you change Q2, that's not going to modify the value of electric field here, which is the same. We already did that, right? So you can answer that question really easily. Like if now Q2 is 10 microcoulomb, what is F2? It's a one-line calculation because F2 is Q2 times E total, which is the same, right? So the only thing that is changed is what you're multiplying here, right? So in the end, you will get 370 Newton in the northeast direction like this. You don't need to recalculate the electric field because that's independent of what the value of Q2 is. Right, so I hope you start to see the usefulness of this. Any question? Where? The electric field? Three times 9. Well, each electric field is 9 times 10 to the 7. You need to add like you add vector. You cannot just add them together. Remember, electric field is vector. So you need to combine these two together. That gives you this one. But then this one and E3, they point in the opposite direction, so you need to subtract them. So you're wondering why the answer is not 3 times 9 times 10 to the 7. Is this your question? Right. Do you understand it now? All right. So let me try again. E1 is going, E4 is going up. And then E3, E1 is going that way. And each one has the magnitude of 9 times 10 to the 7 Newton per Coulomb. So when you add these two vectors together, what's the answer? Well, the answer is not 2 times 9, right? Because you have to add like you add vector. So you need to put E4 here and then draw the vector from the beginning to the end like this. Right? So it's not just adding the number together, and it's a very good point that you brought up. This is very, very important. Electric field is vector. You need to add them like vector. You cannot just add the number together. Right? So in this case, you need to do, like the Pythagoras kind of like right triangle kind of thing. And then you're going to find that E4 and E1 together give you this vector, which point in this direction. And the length is actually going to be square root of 2 times 9 times 10 to the 7. But we are not done yet because we still need to add E3. But E3 is pointing down like this. So how do you add E3 to this one, the red one? Well, you also cannot just add 9 times 10 to the 7, right? Because they point in the opposite direction. So in the end, when you add E3 together, the resulting vector is just going to be this one, which is shorter, pointing, in a northeast direction. And that's how I got this number. Is this clear now? Okay, good. All right, so I hope this is also clear for everyone. Like, remember, this is usually the thing that most of you will miss in the exam. Okay, it's vector, okay, vector. You need to add them like vector. Another question is like, can we also break E3 into X and Y direction? Yes, absolutely. So it's your choice. You can either do it this way, which is fine with me, or you can just say, okay, it's in the I direction or X direction this much, or Y direction that much. It's the same thing. Okay, as long as you realize that you need both direction and magnitude, it's fine. And how do you specify those two is entirely up to you. All right? Okay, so very good. Now we're gonna move to a slightly different thing, but it's gonna be, of course, relevant to this electric field calculation later. So we're gonna talk about a generic object that we see in daily life, because most of the time you're not gonna be dealing with just charge, particle, electrons or protons. Most of the time we don't we don't do experiment with, well, that's not true. Most of the time in our daily life we don't see electron or proton because it's just so small, right? So most of the time we deal with a little bit larger object, like a sheet of metal, or like a spherical ball of metal, or some non-metal like insulator or something like that. So I want to talk a little bit about like what is what we call like a conductor or an insulator. So those two things. So most of the object that we see or use in real life can be categorized into three types. Well, there are many ways of characterization, right? Because you can use, chemical property, you can use physical property, you can use also, the state, whether it's liquid or gas or solid or something like that. So if you use the electrical property, to describe or categorize material, you're gonna have three things. The first thing is what we call a conductor. Conductor can mean many things. In this case, it's the thing that can allow electrons to move within that material almost freely. So you probably remember we talked about an atom last time. An atom consists of nucleus at the core and electrons around it. So at the core, usually you have a few protons and a few neutrons, and electron is going around. But remember that electron is the one which is very light. It's 2,000 times lighter than proton or neutron. So when it's really light, it can move really easily, right? So conductor is the one that allows electron to move freely within the material itself. And usually it's gonna be metal that has this kind of property. So I think every metal is a conductor, I think. I can't think of any metal which is not conductor, because yeah, I don't think there's any. Okay, so most of the time when you talk about metal, you can just safely say that, okay, it's a conductor. So electron can move freely within, this, you know, material or bulk of material. So if you have like a block of aluminum, right? So I think most of you have a laptop which is made from metal aluminum. So that piece is a conductor. Okay, so electrons can move around freely within that material. Well, the opposite of a conductor is called an insulator. An insulator, like it says, it does not allow electron to move freely. It doesn't mean that there's no movement or of any charge at all. That's gonna be kind of, well, if that's the case, then you cannot make, an insulator to be electrically charged. But we know we can do that. But it's just that electron cannot just move from one end to the other end without anything happening. That's not gonna be the case for an insulator. And you're gonna see that in a few moments. But what insulator? Well, most of the time you can safely think that it's, rubber, ceramic, plastic, something like this. Okay. So any non-metallic stuff usually is an insulator. Now I say there are three kinds, right? So what's the third one? The third one is called a semiconductor. We're not going to talk too much about this, but this is extremely important. So it's kind of, I don't know what's the proper scientific word. So it's kind of allowing electron to move, but not much. Okay, so it's kind of like halfway between conductor and insulator. And we have only a few elements in the periodic table that behave like semiconductor. So one is silicon, the other one is maybe gallium, something like that. But silicon is the one that used most of the time. So just briefly, what is so important about semiconductor? Well, the fact that it's kind of allowing electron to move, but not much. It means that we can control how much electron gonna move very easily. Sometimes we want that. So think about a conductor. Conductor, it allows electron to move freely all the time. So it's really hard to, to turn down that freedom of the electron if you think about that in that way. Right? So it's going to move really fast, freely all the time. And if you say like, hey, slow down a little bit, it's very hard to do with a conductor. And for an insulator, it's the other extreme. Like it doesn't move at all. And then you say, can you please move a little bit? That's also very hard to do. But so for semiconductor, it's kind of like moving a little bit already. It's kind of like, like when you wake up in the morning from the bed, right? You're kind of like almost getting up already, so it's easier to kick yourself off the bed that way. Something similar here, right? Semiconductor is, electron is kind of like almost free. It's moving already, but not much. So it's easier to push it to be moving a little bit faster. It's also easier to maybe like slow it down a little bit. So this control allows us to make various kind of device based on semiconductor. And that's why it's probably the most important kind of thing for the past, like 30 or 40 years. Like all the computer, technology is based on semiconductor. Okay, so without that, nothing is possible. Your smartphone is not possible to make. Your laptop computer is not possible to be made. But unfortunately, we're not going to spend any more time talking about semiconductor. That's going to be in other courses for some of you. But just realize that there's this semiconductor also. Okay, so most of the time in our course, we're going to talk about either a conductor or an insulator. So there are a few implications which is attached to being a conductor or an insulator. So I'm going to talk about it now. So a conductor, again, is something that electron can move around freely. So let's imagine something like this. When you have, a bulk of something, let's say copper, which is a metal, and clearly it's a conductor. So electron can move freely inside this chunk of copper. Let's say I put in a few electrons inside here. Electrons are negative charge. So I have a lot of negative sign here. So what's going to happen? Well, when I put in electrons, that's going to look really weird. Maybe I just keep it like this. So when I put electron like this, right? So electron and electron gonna repel each other because they have the same sign. Right? Negative charge repel another negative charge. And this electron will also repel this one. This one will also repel this one. So let's say I put in here like 5 electrons. They're gonna repel from each other, trying to get away as far as possible from the other electrons. So this electron will move that way, this electron will move that way, move that way, move that way, move that way. So eventually what's gonna happen? Well, electron can keep moving, but at some time it's gonna hit the boundary, so it's gonna be at the surface. And usually there's nothing else it can do. So once the electron is at the boundary, it's stuck there. So this is what happened for a conductor, is that no matter how many charges or how much charge you put in to the conductor, the charge will distribute itself at the surface of the conductor. So conductor has the first property that any charges will be only at the surface. Because that's the furthest away they can getting away from the other charge. So charge will always be at the surface. So that means you go inside, there's not going to be any charge here. So Q is going to be 0 inside the material, right? So charge is going to be always only at the surface. Okay, that's the first thing. The second thing is that the electric field inside a conductor is always 0. So E field inside the conductor here will always be 0. And you can see why that's the case, because remember that even though there's no charge inside the conductor, it doesn't mean there's no electron inside the conductor. It's just that the electron inside the conductor is balanced out by the number of protons. So in total, it's electrically neutral. Okay? So this is a very important point. So think about this. I say that charge will always be at the surface. Okay? But it doesn't mean inside the material itself there's no electrons or no protons, because it's still there, right? It's just neutral. But imagine that if you have electric field inside which is not 0, what's going to happen? Well, if electric field is not 0, then the electron at that position will feel some kind of force, right? According to F equal to Q times E. So because there's a force on that electron will start to move towards the surface. So this will happen until in the end, electric field in the center inside the conductor is 0. So there's no movement anymore. So it's kind of like, self-adjusting itself such that the electric field inside the conductor is always 0. So that's kind of like the rough reason why electric field inside the conductor is 0. So these two kind of facts are very important later on. Okay, so I'll just write it down here. What about insulator? Well, for insulator, there's really no such a thing. So for insulator, let's say rubber, you can put the charge anywhere, inside, outside, they're not going to move, right? So no movement of charge. So that means you cannot say that charge will be at the surface of an insulator. And inside an insulator, E field is not necessarily 0 inside an insulator. So it's very different behavior. So you need to be very careful when you read a question, right? Whether it's talking about a conducting sphere or an insulating sphere, because the term conductor or insulator gonna tell a very different story because they just behave a little bit differently. All right. So I have two quick things before we finish to talk about. So far we have talked about the electric field from a point charge, and we know how to write that down already. So if we have an electric field, a charge, let's say Q1, and let's say positive, and we want to find the electric field at this particular location, so we know that it's going to point away. So electric field point in that direction, and the magnitude is given by kq1 divided by r squared, where r is the distance between the point charge to the location that you're interested in. Okay, now what about not point charge? You need to calculate it, of course, and we're gonna maybe talk about that next time. But there are special shape of object that give a very similar result, and that's gonna be a sphere. So if you have a sphere of charge, SPHERE, sphere, and let's just be a little bit more explicit. Let's just say it's a conducting sphere. Conducting sphere, and the total charge is plus Q1 still. So remember that a conducting sphere will distribute the charge around the surface, right? So now the charge is not point charge anymore. It's just gonna be plus charge evenly distributed on the surface of this sphere. So if you count all the positive charge around the sphere, around the surface of the sphere, you get plus Q1. Okay, so that's what I mean by conducting sphere of plus Q1. Right? So the charge is evenly distributed around the surface area of this sphere. Now for this sphere, if you talk about the electric field at the distance r away, measure from the center of the sphere, okay, not the surface, okay, at the center of the sphere. Then electric field will also point out, and electric field will also have exactly the same magnitude. Okay, but remember this is only true for a sphere. If you have like a cube, then this is not the case. Okay, this is only for a sphere. It's not trivial at all to show that this is the case. You need to do some calculus integrating stuff. We're not going to do that because the math is too complicated. But as a fact, you need to, you can remember that for a sphere, the formula is the same as point charge. Now the problem is that if you talk about the electric field at the point, but that point happened to be inside the sphere, is electric field still given by this? Of course not, because we know that if it's a conducting sphere, then electric field will be zero inside. Okay, so that's the difference. So when you plot, the strength of the electric field as a function of distance for point charge, it's going to be stronger and stronger when you approach the location of the charge. So it's going to look like this. But for a sphere, because at some point you're going to be entering the inside of the sphere, that when the electric field is 0. So outside the sphere is behave as if all the charge is at the center. It's the same formula, right? As long as the point that you're interested in is outside the sphere. But inside, suddenly, the electric field drops to 0. So the graph looks something like this. And then suddenly it drops to 0. This is big R, and big R is the radius of the sphere. Okay, so outside you don't see any difference, but inside the sphere, the electric field must be 0. So that's the difference. So be careful about this. Now, what about if we talk about conducting sphere, not conducting sphere, a sphere but an insulating sphere, so non-conductor. So insulating sphere, where the charge is evenly distributed everywhere in this sphere. Now, because it's insulating sphere, the charge doesn't have to be at the surface anymore, right? Because, the charge cannot move. So somehow, let's say we can evenly distribute the charge Q1 all over the meat of this sphere. So think about, like a bowling ball or something like that, and the charge is everywhere inside the bowling ball. And the total charge is Q1. So what is the electric field? So it turns out that the electric field, if you're outside, is still going to be the same formula if you're outside the insulating sphere. But inside, it doesn't have to be 0 any longer because, why? Well, it's not a conducting sphere, so there's no reason for it to be 0. But outside is the same formula. So outside, they look the same thing. So it's 1 over r squared. But it can be shown, and we're going to show this later when we study what we call Gauss' law, that the electric field inside is going to be actually linear, like this. And this is going to be r, which is the radius of the sphere. Okay, so this should give you kind of like a preview on, how different kind of material going to behave differently for the electric field. But if all of them are sphere, then outside the sphere, actually the electric field have the same formula, which is 1 over r squared. Right? So this region here, and this region here, and this region here, you cannot really distinguish whether it's a point charge or a conducting sphere or an insulating sphere. Right. Okay, that's all I want to talk about for today. So I will see you on next Monday then. All right, take care everyone and see you later.